It's my pleasure to welcome the second changemaker to the stage tonight, Shuaishuai Yuan. Shuaishuai is a PhD student in the Department of Mining and Materials Engineering working with Professor Kirk Bevan. And Shuaishuai is going to talk to us tonight about how we can design better batteries from the atomic scale up. And she's going to tell us about Polarons, which is a new concept for me, and I'm sure also for many of you, and these Polarons are very important in determining the electrical properties of advanced materials that you'd use both in batteries but also in a variety of other renewable energy technologies. Ready? Okay, so with that, Shuaishuai.
Thank you. Every day, we use different kinds of electronic devices. A laptop, a mobile phone, a tablet. But we are never satisfied. We always want the devices to somehow run faster, but at the same time, smaller and lighter. One of the things particularly we're not satisfied about is rechargeable batteries. We want to have better rechargeable batteries inside the devices that is longer lasting, but at the same time, smaller and lighter. The batteries inside these devices are called lithium-ion batteries. Lithium-ion batteries power everything from electronic devices we use every day to the electric cars. In the electric cars, the weight of the battery, the capacity of the battery is especially more important because they determine the speed and the driving distance that we could achieve. Imagine if we can improve these batteries, our life will be much easier. We don't have to charge our phone every day, and we can drive our electric cars without range anxiety. How satisfied is that? Scientists and engineers have tried many alternative approaches to battery chemistry and design in order to get smaller, longer lasting, and more powerful batteries. One of their trials is on Lithium-Air battery, because this Lithium-Air battery has far higher energy per mass than the conventional lithium-ion battery I have just mentioned. The reason for that is, at negative electrode, there is only lithium, the lightest metal in the world. And at positive electrode, the reaction is a reduction of oxygen supply from air, which means there is almost no weight at all, because oxygen is not stored in this battery, it is just from air. Practically speaking, this saves a lot of weight, but it also brings us its own difficulties. For example, when the car is running, the battery is in the discharge process. During the discharge, oxygen reacts with lithium plus ions to form lithium peroxide. And as the battery is discharging, more and more lithium peroxide is formed in the pores of this electrode. And when all the pores are filled up, no more lithium peroxide can be formed, and the battery is empty. However, the problem is right here. If we zoom in this part, the blue part, lithium peroxide, is a very bad electron conductor. Electron cannot even go through this material very well, which will dampen the whole reaction and eventually kills off the reaction and kills off the battery's power. Some people refer this as sudden death. The battery is not working suddenly. How dangerous it is for a car. Electron transport is the main limiting factor of the battery performance of this lithium-air battery. Firstly, we have to understand the electron transport mechanism in this discharge product, lithium peroxide, and then we can think of how we can improve this. And in this talk, I would like to invite you to come with me to go further into this atomic world materials. And let me introduce you how we look at these materials at an atomic scale and how we design materials with atomic scale. Well, more than 1 million times zoom in. Welcome to the atomic world of materials. If our eyes are as good as electron microscope, we will not see this material as a bulk. We will see this lithium peroxide is composed of lithium atoms and oxygen atoms, and we will be amazed how neatly they arrange themselves. The order arrangement of atoms is called crystal structure. Crystal structure is very important in material science because they determine the properties of materials. And in this lithium peroxide, the red balls represent oxygen atoms, and they are paired up. The bonded oxygen pairs play an important role in the conductivity of this material. And the green balls represent lithium atoms. We can view this lithium peroxide as bonded oxygen pairs embedded in the sea of lithium plus ions. Knowing this crystal structure is also very important to our simulation work because they serve as an input. With this input, we can get lots of output containing materials properties. So at this point, let me briefly introduce my simulation method. My simulation method is called first principles calculation. The name of this method also fascinates me a lot. It is called first principles calculation because it does not depend on any external parameters except atomic numbers. For example, in this calculation, I just need to know I have lithium atoms and oxygen atoms to start. So it is parameter-free. And also, this calculation is based on quantum mechanics. Briefly speaking, we know that solids are made of electrons and nuclei. If we can model the basic interactions of electron and nuclei accurately, then we can get all the properties of solids emerging from this first principles calculation. Generally speaking, we have crystal structure as an input, and then Schrodinger equation is solved by supercomputers. And finally, we can get output that can predict materials properties quite well, including electronic structure I will talk about very soon. With these very cool first principle calculations, we can go further into the atomic world and see the electrons. What will happen if an electron is injected into this material? This is one of our simulation results. The yellowish cloud represents electron density. And at the beginning, electron is everywhere. But then it becomes more and more localized. And finally, it localized at only one place. This localized electron has a name. We call it a polaron. What is a polaron? Polaron is not a new concept. The theory of polaron has already been developed for about 8 decades. We know that the electron move freely in metal. However, in some materials, the electron will be trapped, and it will push the surrounding atoms away from their equilibrium position. The trapped electron, together with the surrounding atoms, we call it a polaron. Polarons move slower than free electrons because it has to go over lots of barriers when moving. It is like driving a car on a bumpy road. The speed of the car has to be slower. Similarly, polaron hopping will greatly affect electron mobility, so it will influence electronic properties of many kinds of materials. Many research has focused on the part when the polaron has already formed and they move by polaronic hopping, while my research focuses on the initial stage of polaron formation. That is the transition process starting from free electron until the polaron is formed. And how long does it take for a polaron to form? It is in femtosecond scale, a very short time. Though this time is tiny, this time is still varies in different materials and under different situations as shown in my study. In order to study this fast transition process, we have to first know how to track these polarons. Unlike normal things, we cannot just see or measure polarons directly, but we have some ways to characterize polarons, and today I will refer them as footprints. Now I will introduce you 3 footprints of polaron formation. The first footprint is electron density. We have just seen a video. At the beginning, the electron is delocalized. It is everywhere. And after a while, it becomes localized at one place and the polaron is formed. So electron density is the first footprint of polaron formation. If the first footprint helps us to understand where polarons are in the space coordinate, the second footprint will help us to understand where polarons are in the energy coordinate. And here is one of our simulation results. But explaining that is a little bit complicated, so let me use an analogy. Electron states are like seats on the bus, and electrons are passengers. And in this bus, the front seat have lower energy, and the back seat have higher energy. When an extra electron gets on the bus, it behaves a little bit differently as human beings. First of all, it will run around at the back of the bus, and then it will gradually move to the front. And finally, it comes to the front and pick one particular seat. That indicates a polaron is formed. So this density of state is another footprint of polaron formation. The third footprint is stretching of bond. That is the most straightforward one. Oxygen bonds are like springs vibrating around a certain equilibrium position. When the extra electron is delocalized, the bond remains unchanged, and they are about the same length. However, when the electron is localized at one of the oxygen pairs, that pair elongates dramatically. So this bond stretching is the third footprint of polaron formation. With the three footprints I mentioned above, we can explore more of the initial stage of polaron formation. For example, with this bond stretching, we can try to estimate the polaron formation time. In my study, the time period for bonds stretching from 1.6 angstrom to about 2.2 angstrom is defined as polaron formation time. We ran the simulation many times in different materials or under different situations to study this time. One of the studies is I do exactly the same simulation with the same material, but under much lower temperature. We see this time changes a lot. It took a much longer time for a polaron to form in lower temperature, which means the polaron formation time is temperature dependent. In our study, we also show that this time changes in different materials. And why do I study this time? And why is this formation time important? Because if we can understand this time better, we can know how to tune this time for different applications. For electronic devices, we want to accelerate electronic conductivity. So we need to promote free electrons because free electrons move faster. That is, it is better if there never forms a polaron or slower to form a polaron. In the contrary, if we would like to design some protective corrosion-resistant coatings, we would like to decelerate electronic conductivity. So we want to stabilize polarons, which means we want polarons to form as quickly as possible. Tuning this time can be achieved by designing materials at atomic scale. That is a bottom-up design I'm going to talk about. Let me give some examples of bottom-up design in lithium-air batteries. In order to enhance charge transport of lithium peroxide, one modeling study replaced some lithium atoms with silicon atoms. It is called doping of materials. That is intentional adding impurities to enhance materials' properties. This proposed tailored new material is expected to show significantly higher electron mobility. Similarly, in some experimental study, the capacity of lithium-air batteries is significantly improved by simply adding chloride ions into the electrolyte. The chloride incorporated lithium peroxide film is shown to have higher conductivity, so as adding nickel ions, cobalt oxide ions, barium ions. And our simulation work can try to rationalize how these doped ions can improve charge transport, and we can also try to provide some guidelines for future experimental study. This atomic scale modification, though looks like insignificant, but will finally have the power to significantly improve performance of devices as we zoom out to the scale to our real life, such as try to find a cure for the sudden death of lithium-air batteries. In today's journey to the atomic world, we have come a long way from macro scale, the component of devices, down to atomic scale. And when we design materials, we do the opposite direction. We design materials with bottom-up perspective, starting from atomic scale and work our way to the macro scale. And as we are closing to the end of this talk, I would like to mention that Polarons is not only formed in this lithium peroxide. It has reported in almost every metal oxide, organic semiconductors, and amorphous materials. We notice that these materials are often used in many kinds of energy devices, such as solar fuel cells, different kinds of batteries, organic solar cells. Understanding polaron formation is a necessary step to help improve electronic or optoelectronic properties of these energy devices. My research won't give you those high-performance devices right away, but it focuses on studying energy materials from a fundamental perspective. I try to understand electron transport in the discharge product of lithium-air battery, and more specifically, I try to understand the polaron formation in energy materials. It might be only one of the missing pieces in realizing the sustainable development. But I believe if all of the scientists and engineers and all of us working together towards the same goal, I'm sure the high efficiency, more stable, cheaper new energy devices, and the sustainable development of our society will not be a dream anymore. Thank you.
Thank you, Shuaishuai. So we have time for one or two questions at the back again.
Thank you for that excellent talk. It was really fantastic. Just a simple question. Have you looked at contamination of water vapor?
Water vapor? You mean from the lithium-air battery, or?
The biggest problem with lithium-air is water vapor contamination.
Yeah, for the study I'm studying, my lithium-air battery is in the aprotic electrolyte, so it's not a lithium water battery. But I think there will be many research studying on that kind of thing.
Any other questions? Okay, if not, let's thank Shuaishuai again.